All right, let's jump right into this explainer. Today, we're exploring a concept that honestly sounds like pure science fiction, but I promise you it's entirely real and it's happening right now. We're looking at how microscopic biology, specifically ancient strains of bacteria, is stepping up to solve one of humanity's biggest and most expensive infrastructure problems. Get ready because we're talking about a literal living infrastructure revolution. So I want you to start by just asking yourself this. What if concrete could heal itself? Really think about the implications there. Our modern world is practically built on concrete. It's the most widely used construction material on Earth. But it has a fatal flaw, right? It cracks. What if, instead of sending out crews with heavy machinery to constantly patch those cracks, the concrete itself just sensed the damage and grew back together?
Section 1. The concrete cracking crisis.
Look, traditional concrete is an incredible material, but it's virtually guaranteed to fail over time. It always starts with these tiny, inevitable stress fractures. This happens from things like plastic shrinkage as the concrete dries or thermal expansion during hot weather. Now, on their own, these microcracks might seem totally harmless, but they create pathways. Water seeps into the concrete, bringing harmful chlorides right along with it, and that leads to what structural engineers literally dread most: rebar corrosion. The steel reinforcements inside the concrete begin to rust, they expand, and they shatter the structure from the inside out.
And the financial toll of all this degradation is just absolutely staggering. The American Society of Civil Engineers estimates there's a multi-trillion-dollar infrastructure funding gap in the U.S. alone, with a massive chunk of that dedicated simply to concrete maintenance and patching. Across the Atlantic, it's no better. The European Union spends between 4 and 6 billion euros every single year just maintaining their bridges and tunnels. It's a massive economic and environmental burden. We urgently need a better way.
Section 2. A microscopic solution. Enter biomediated healing, or simply bioconcrete. This is concrete that has been engineered with dormant bacterial spores, specifically strains like Bacillus and Spirosarcina, along with a nutrient source like calcium lactate mixed right into the batch. These microscopic builders just sit there, completely asleep, locked inside the dry concrete. They wait patiently. But the second a crack forms and water enters, they wake up, feed on the nutrients, and autonomously precipitate calcium carbonate, which is essentially limestone, to seal the crack completely shut. Okay, let's dive into this and compare the natural limitations of concrete against our vastly superior bioengineered solution. Naturally, unhydrated cement particles can react with water to heal tiny cracks in a process called autogenous healing, but it's super limited. It can only handle the most microscopic of fissures. With biomediated healing, it's a whole different ballgame. The bacterial capsules activate, they consume their nutrients, and they pump out massive amounts of calcium carbonate, aggressively filling in much larger cracks. It really is a vastly superior process.
Section 3. The healing mechanism. It all happens in this beautifully elegant 5-step chain reaction. Step 1. A crack forms in the structure. Step 2. Environmental water naturally seeps into that crack. Now, step 3 is where the magic happens. That water is the actual biological trigger. It dissolves the protective carriers and wakes those bacteria right up from their dormant state. In step 4, the activated bacteria start consuming their food and multiplying, triggering a process called microbial-induced calcite precipitation, or MICP for short. Finally, step 5, the minerals accumulate, the crack physically seals itself, and the water is blocked from going any deeper.
And this brilliantly illustrates the biochemical pathway itself. Some of these bacterial strains actually use an enzyme called urease to catalyze the breakdown of urea. Following the chemical equation, this process produces carbonate ions. Those ions then react with calcium present in the environment to form solid calcium carbonate crystals. It's basically an autonomous biological manufacturing plant turning raw nutrients into solid rock right where the structure needs it the absolute most.
Now, what's really interesting here is the undeniable visual proof from actual lab tests. When you look at a visible damaging crack in a piece of concrete and then compare that to the exact same spot just 28 days after water exposure, it's mind-blowing. The bacteria have literally filled the gap with white calcium carbonate crystals. It didn't require a repair crew, it didn't require injected epoxy. The material just heals itself.
And we're not just talking about fixing microscopic hairline fractures here. Research shows that specific urealytic bacteria can effectively seal cracks up to 1.0 millimeter wide. Now that might sound small to you and me,
But in structural engineering, a 1 millimeter crack is a massive structural vulnerability. In just 7 days, the bacteria can close these gaps, leading to a staggering 70% reduction in water permeability. The water simply can't get in anymore.
But it's not just about plugging a leak, right? It's about structural integrity. The strength recovery data is equally impressive. When traditional, untreated concrete cracks, it might naturally recover about 7.41% of its compressive strength. But the bioconcrete, it recovers an incredible 30.13% of its structural strength. The material doesn't just look fixed, it genuinely rebuilds its own load-bearing capacity, which fundamentally extends the life of the entire structure.
Section 4. Protecting the bacteria.
So the crucial point we have to address is that wet concrete is a spectacularly harsh environment for living things. The mixing and curing process creates a highly toxic, extremely alkaline environment with a pH of 12 to 13. Plus, once it's cured, it's incredibly dry. If you just dump naked bacteria into a cement mixer, the crushing mechanical shear forces and that toxic pH will kill almost all of them immediately.
To solve this, scientists essentially had to invent microscopic bunkers to protect our tiny builders. They've developed these incredible carrier systems. By encapsulating the bacteria and their food in materials like porous expanded clay, polyurethane microcapsules, hydrogels, or silica gel, the bacteria are totally shielded from the crushing forces and the toxic pH. In fact, research by Dutch inventor Hendrik Skongs showed that when packed inside special clay pellets, these bacterial spores can remain dormant and perfectly viable inside a concrete wall for up to 200 years.
Let's move to how this builds into the cutting-edge realm of nanobiotechnology. Scientists are actually using magnetic iron oxide nanoparticles to solve this protection challenge. Because bacterial cell walls have a negative net charge, these nanoparticles physically adsorb onto the cell wall, essentially wrapping the bacteria in a suit of magnetic armor. This amine-modified nanoparticle coating not only protects the bacteria from the harsh concrete environment, but actually promotes bacterial growth once they activate, massively improving the self-healing efficiency.
Section 5. The future of infrastructure. The global macro impact of this technology is just astounding. By the year 2034, the global bacteria-based self-healing concrete market is projected to reach approximately $1.98 trillion. That's driven by an extraordinary 37.5% annual growth rate. Why? Because the total cost of ownership over a building or bridge's lifespan just plummets when you eliminate the need for constant human repair and drastically extend the life of the asset. And the applications are expanding so rapidly. We're talking about retrofitting marine structures where saltwater corrosion is incredibly destructive. We're looking at integrating this bioconcrete with smart IoT sensors. Imagine a bridge that detects its own crack digitally, reports it to the city's network, and then biologically heals itself before a human crew ever gets dispatched. But most importantly, the construction sector accounts for roughly 39% of global energy-related CO2 emissions. By creating structures that last decades longer without needing energy-intensive patching or replacement, bioconcrete becomes an absolutely critical weapon in hitting global decarbonization targets. Which leaves us with this final provocative thought. For thousands of years, humans have built with static, inanimate stone and cement. But what if the cities of tomorrow aren't just built? What if they're cultivated? If our roads, bridges, and skyscrapers can bleed, scar, and heal just like we do, it really begs the question, what other biological miracles can we weave into the very fabric of our cities? The future of construction is alive, and it's happening right beneath our feet. Thanks for joining me on this explainer. I really hope you found this as fascinating as I do.